אוקיי? כאילו, אם אתה לא יודע שום דבר על התנסות, לא יודע שום דבר על אקסימנטל או כל דבר כזה, ואני שואל אותך עכשיו לאן הסדרה 1 חלקי n מתכנסת, תגיד לי, אפס, כאילו, כנראה, אתה מבין מה כאן, אבל השאלה פה זה האם אתה יכול להגדיר את הדבר, את האינטואיציה הזאת, בצורה שאשכרה קוהרנטית.
כן, באמת יש עבודה.
אני חושב שהרבה ברור כאילו, התשובה היא ברורה, שאלה אם כאילו יש כללים שאשכרה אפשר להגיד לא חד וחלק נכון, או שאין תשובה.
אביב, שומע אותנו טוב? רואים אותנו טוב?
כן, שגם בפיזיקה כאילו.
כן.
כאילו תורת שונות שהשאלה זה לא האם זה נכון, אלא האם אתה יכול להגדיר את זה ככה שזה כאילו השכרה קוהרנטית. כאילו נגיד את התשובה כבר.
מישהו מהעברית.
אז פעם שעברה, last time, unfortunately, we met only in an online format. And the last thing we did was, so I see that, so last time we showed that for maps from an operator system to C of X, positive if and only if completely positive, and also like this. So I think this was the last thing we did last time. This was easy. I mean, here you only need to prove it for states somehow, like for functionals, and then automatically just compose it with the point of evaluation and you're done. But this was for this we needed a partition of unity, but then it was fun. And I want to maybe mention. Okay, so first thing I want to do is to have a corollary. So corollary. There are a few corollaries. One is, do you remember that we also spoke about the map? Okay, maybe before corollary. Also, we showed there is a positive map, linear map. So also we showed for every t contraction, namely in the unit of b of h, there is a positive map, which I think I called rho sub t from continuous functions over t into b of h, that maps such that for every two polynomials p and q in C of Z, it maps rho of t of p plus q is p plus q bar is pt plus qt. Right. And I promised you that the theory, so we proved that there is a positive map that does it, and I promised you that the right theorem should be there exists a completely positive map that does it, or UCP map that does it, but with this, right? So corollary, this rho sub t is in fact UCP. Okay. And you should think of it as a sort of counterpart to what we can do with the unitary operator. But then we get a star morphism, right? From the continuous functional code. Okay, so another corollary from this corollary is the following one. Well, sometimes people call it the matrix valued von Neumann inequality. So if I get a n by n, like a matrix of polynomials, then and T in a contraction in U of A, then Bij T, this matrix, giving square sense of this matrix, its norm is less than or equal to this primum of Z to 1 of I mean, right, this is so when n is equal to 1, this is the good of the von Neumann inequality. And here we have like if you want a quantized version of it, like for basis. Okay, and we have it because the map is in fact not only positive, it is competing. So proof is follows. And by the previous corollary plus the fact that UCP is UCC. Right? Okay. So I would like to learn a little bit where I'm going to. So this was just something we had needed to do last time and we didn't have time. Wanted to say it. So there are a few directions. Essentially, my goal is that next time we'll be able to do a so-called Harrison's extension theorem that allows us to extend UCPs, like to have some sort of a Hahn-Banach theorem for UCPs. By the way, do we have a sort of Hahn-Banach theorem for positive maps, for unital positive maps? So, okay, let me rephrase the question. Is it true that whenever I have, okay, I mean, if you write it in your notebook, it will look like something that is completely unrelated, but just ask me a question. If we're in a situation that S and T are operator systems, and S is even S is a sub-operator system of a sister algebra A. Okay, so it's a sister algebra, S is an operator system, and I have here a map to a unital positive map to another operator system, even to some B of A. Very simple. Can I extend this? So in fact, we prove that we can do it if H is one-dimensional, right? If H is one-dimensional, then this is something we did a lot of time, like to extend states. How do we do it? We say that unital positive map is equivalent to unital contraction. Then we use the usual Hahn-Banach. We extend it to unital contraction. then unital contraction on a sister algebra is a state which is positive, therefore it's unital positive. So if H is one-dimensional, the answer is yes. But in fact, what is hidden here is that, this is something we're going to do next time, not this time, that we can always do this for UCP maps. And when H is one-dimensional, then this is automatically UCP, because this case, the range is commutative. So, but in general, can we do this? And you should know the answer.
Okay.
Because I said you should know the answer, right? Yeah, you're not thinking about it.
Don't know.
Ah, okay. You have a question?
No, I'm just.
So it's one of the examples, the special example I showed you last time.
What is Arvidson's example?
Arvidson's example. So what was Arvidson's example? Arvidson's example was a specific operator system S, which was a span of 1, Z, and Z bar inside continuous functions over the circle. And we show that there is a map from it to M2, 2 by 2 matrices, which we can think of as right as B of C to the 3. Such that, so this map was very natural, but we did it last time. And this map was unital and positive, but its norm was 2. However, we also said that for any sister algebra and a unital positive map, or even in the commutative case, yes, we have this thing, positivity is equivalent to complete positivity. So this map will be UCP, hence UCC, and contraction. So it can't have a norm 1 that this map, this extension file, can't have norm 1 here and norm 2 here, right? So okay, so I answered the question. No. But we're going to have, so we're going to have this Arvidson's extension theorem, which is going to tell us what happens when the maps are UCPs, and then we'll do such an extension. It is very useful. We're going to use it in the third part of the course. So this is one thing, one big thing we should do. Another big thing we should do is to prove and to discuss about Stein-Sprague dilation theorem, which is the theorem I promised you that is the generalized GNS. GNS tells us that whenever we have a state, we can dilate it to star representation. GNS tells us that whenever Stein-Sprague tells us that whenever we have a UCP, we can dilate it to star representation, and the GNS is only a private case, and this is something we're going to do today. And here and there are also small things I would like to like small fruits I would like to have for later discussions. Okay, so I will do it. So I hope to do the Stein-Sprague dilation theorem, let's say, in half an hour from now or 45 minutes. But right now, there are more things I would like to say. So, okay. First, we discussed about the special cases where the range or the domains are C of X, are commutative sister algebras. Now, whenever you have a theory, like you do something in operator theory, there are two cases you want to check in your hands. One is of abelian sister algebras, commutative sister algebras, and the other is like the other best thing, which is matrices and bad matrices. So my question is, what happens if I take here n-band matrices instead of C of X? Do I have such a theorem or something similar? Another way to think about it is the following one. So special cases of this tell us that S to C, positive if and only if completely positive, and C to S. positive, completely positive. Now we can like quantize this, and in mathematical physics language, and consider these guys. What can we say about them? So, okay. So this guy is a big deal or mediocre deal. And I'm not going to speak about it today, but next time. Okay. This one is very easy, and I will leave it as an exercise, but I will explain what is the exercise exactly. So let's do this. Okay, so exercise. A, well, the first thing you need, like it's like a hint if you want, not an A, but let's call it A. Show that so let A be a sister algebra. A, show that whenever I take a positive n by n matrix over A, T. Then A is the T is the sum of n positive matrices of the form AI star AJ for some n elements. So these are clearly positive matrices. Why? Can you see why? So why is such a matrix is positive? Because you can write it as something star something. You just need to understand what it is something, but it's easy. And then the fact that you can write any n by n matrix as a positive sum of these is also not a big deal. You just write this as rows, and then you think of this matrix as a sum of like matrices that are just rows and then zeros everywhere. And okay, do it. And it's easy. It's a linear algebra exercise, but only with entries in A inside instead of C. And then using this B, this is exactly what I wanted to say. This was originally a theorem of Choi, but it's an easy exercise once you do A. Let phi be from Mn to S. The following are equivalent. 1, phi is completely positive. 2, phi is n positive. N positive means that just phi n is positive. So this is enough. And 3 will help you to prove that. So of course 1 implies 2 is immediate, right? If you're completely positive, then you're and k positive for any case, specifically you're n positive. 2 imply 3 will also be immediate, and then 3 will imply 1 will be the only thing you need to prove. So this is that phi of the matrices Eij, this matrix is positive in that's. So Eij, you know what we mean by that, right? 1 in the ijth entry and 0 elsewhere. Okay. So of course, if you are n positive, okay, yes, I didn't write which image. Maybe I should have a size. Bij, I don't know. N. Okay, so it's n by n. So this is an n by n matrix, and this is nothing but phi n acts on an n by n matrices in Mn.
This is true over MNC, right?
Mn is MNC.
Oh.
So this is something I said a few times. Whenever I write Mn without nothing, I mean Mn of C.
Right.
Okay. So you understand what I'm doing here? If not, please ask. But, I mean, here just Eij is an n by n matrix. Phi of Eij is something in S, but I'm running over all Eij, so I'm getting here and something in Mn of S. And I'm just saying, I'm telling you why 2 implies 3. 2 implies 3 because this is in fact phi of the n by n matrices, the n by n matrix with entries in Mn, each of them is Eij. So this is just phi n of E11, E12, until E1n, etc., etc. So of course, and this matrix is easily, I mean, it's clearly positive. That's an easy exercise. So you know it's spectrum. So of course if phi is n positive, then this is positive. So the only real thing you need to prove is that 3 implies 1. But this is fairly. Okay, so this will tell us that phi is completely positive if and only if it is n positive. So that's the answer for these matrices. I can already tell you, so n pos if and only if Cp. This is also the answer to this question, although we're going to do it next time. Okay? And this is kind of useful, I mean, these observations. The fact that you know what happens in the commutative case, the fact that you know what happens in the n by n matrices, gives you something to work with. Okay.
Is so CP map from MNCX S will be like applying a CP map on each evaluation.
Yes, so you can think of it. I mean, so I had here 2 generalizations, right?
They are
the one that the range is C of x. If you take Mn of C of x, in case you're speaking about the range, and I think your question was the other way around.
Yes.
But just saying, I'm answering something else.
Okay.
This is very easy. Yeah. This will be once you know thing for the range, then you just do the trick with point evaluations we did before, and the answer will be that it will be completely positive exactly when it's n positive. And from when you doing the domain Mn of C of x, I think you should be able to do something similar with partition of unity like we did in C of x. So I don't think it's immediate, but maybe with tensor product thing. Okay, maybe it's also immediate by other techniques, but yes, I think it's true. We can think about it. Yes, okay. But at least the one where you put Mn of C of x in the range, this is immediate. Once we have it just for Mn. Okay, now let's do a quick discussion about multiplicative domain. This is also something very useful, multiplicative domains. Then we'll have a quick corollary about conditional expectations, and this is something I will use also later. And then we'll move on to Stein's. Okay, so theorem. Let phi from A to B, these are sister algebras, be UCPs. Of course, unital, if I said UCP. Unital, let R phi be those A in A such that phi A star phi A is equal to phi A star A, and L phi be those A in A such that phi of A star is equal to phi of A star. Then R phi is in fact all these A's in A, such that for every B in A, this should remind you something. Phi B of A is equal to phi B times phi of A. And L phi is same thing. All the B's in A such that phi of AB is phi of A, phi of B. And thus, R phi and L phi are closed algebras. And phi restricted to R phi, phi restricted to L phi are homomorphisms. Verify with yourself that you at least understand the thus. So once we prove this, then of course they're subalgebras. I'm not claiming they're star subalgebras or anything like this. Just saying they're closed subalgebras, and that phi is restricted to them is a homomorphism. Again, I'm not claiming star or anything like this. Homomorphism, namely, it is multiplicative, right? Of course, it's linear. Okay, of course, it's multiplicative, right? That's the way, right? Once you know the place in which they are multiplicative, then they are multiplicative. And okay, we're going to prove it, but before corollary from this, let M phi be the intersection of these guys. So you should read it like this: M phi is the set of all A such to satisfy this equation and this equation. Okay.
That should already be a C star.
So how do you see it?
Because the adjoint of R phi is contained in L phi. Isn't that good?
I mean, you're using the theorem, or
No, I think that if you take the adjoint of R phi, it should be contained in L phi, no? But if you
yes, that's right.
So M phi is a C star subalgebra.
Yes, right. Okay. So you see it automatically, but you don't see it is closed, right?
But
Unless you know that.
no, I
unless you
need to know
theorem.
both of these things to
Yes,
see that
yes,
M
sure,
phi is.
sure. So this is what I'm going to say. So M phi is a C-star algebra, or subalgebra. C-star subalgebra, right? So right. And phi restricted to M phi is a star. Okay, and this should also be more or less clear to you, because what Alon just have said. Well, I mean, it's even easier than that. I mean, it's, here you see that once you're, yeah. So, well, I don't know if it's easier than that. It's good. So it's a star subalgebra, and it is closed into the intersection of two closed star subalgebra, and phi will be homomorphism, but will also respect the star. Okay. So let's prove the. Well, just let me give it the name, definition, terminology. M phi is called the multiplicative domain of phi. And it is a useful notion. Many times when we want to prove something, once we know we have a multiplicative domain, we only need to show. So suppose we want to prove that the UCP is a star homomorphism, we only need to show that every element is in the multiplicative domain. So if you want to prove that something is a star homomorphism, it means that you only need to show that you have these two inequalities, these two equalities. Okay.
Could you repeat why is this defined on homomorphism, like multiplication?
Why this is defined? Because that's the set of all A's, such that for any B.
No, like wait, don't you define it as the previous one?
What?
We're using the theorem, no?
The corollary follows from the theorem.
Okay, so this is all the proof.
No, I didn't start the proof.
Okay.
I'm just saying, once you know the theorem, you know this corollary.
Okay.
And in fact, what I really need is not the theorem. I really want the corollary. In fact, usually what we use is the following thing. We want to prove that the UCP is a star homomorphism, and the only thing we prove is that it satisfies these two equalities. So if I give you a UCP, you know that it is a UCP, and I'm telling you, show it is a star homomorphism, then you can tell me, Guy, it satisfies this, it satisfies that. I'm done. Because why? Because I show that any element in the sister algebra is in the multiplicative domain of phi. So the multiplicative domain is everything. So my original phi was star homomorphism. Okay, this is the way things work. Okay. So in many papers, if you'll open many papers in sister algebras or these things or operator system, you will see people proving like this. They want to prove that something is star homomorphism and they only show these things. They don't explain even, they don't say the word multiplicative domain, just prove this and they're done. Okay, so proof of the theorem. Clearly, so I'm going to prove only the first one, okay, for alpha. Clearly, alpha contains the right-hand side. RHS is right-hand side, okay? So let's need to show this containment. So let's A in R3 and B in A. And by the Schwarz inequality, for phi2 with the matrix AB star. So what is the Schwarz inequality? In general, the Schwarz inequality is something that we proved last time. It tells us that if phi is too positive, then phi of x star phi of x is less than phi of x star x. This is something we proved last time using a very nice lemma. Now I'm going to use it not for phi, but for phi2. So in fact, I'm going to use the full positivity of the map phi. So we're only using now the full positivity of phi. So we have that phi2 of AB star 0, 0 star phi2 of AB star 0, 0 is less than or equal to phi2 of AB star AB star 0. So let's compute it. So this is right. This is on the left hand side of phi A star phi B 0 0 phi A phi B star, and in the right hand we have right a phi of A star A, phi of A star yes, I think why did I write B? B.
You guys just saw it.
I think it's fine. This is A star B star. This would be B A, and this will be B star. I think it's fine. Let's check it anyway. What is there a question?
Yeah, just a small one. So phi is always self-adjoint.
Yes, positive maps are always
Right. Just to make sure.
something we said.
Okay.
And this is nothing but phi of A star phi of A. This is phi of A star phi of B star. This is phi of B phi of A. And this is phi of B phi of B star. Right? But A is in alpha. A is in alpha. So it means that this guy and this guy are the same. So therefore, this matrix is greater than or equal to this matrix. Then we get that this matrix, phi A minus phi B, phi A, and here it's adjoint, effectively phi A minus phi B, phi A star, and you will just have not carry effect phi B star minus phi B, phi star. This matrix is positive. But this is I think I gave you last time an exercise to prove that I don't know, a matrix of the form 1 A star B is positive if and only if A star A is less than B, right? So from this, multiply this by t or something, and then let it go to 0, and you'll see that such a matrix is positive if and only if these guys are 0. This is an easy computation once you know this. So phi of BA minus phi B, phi A is 0. So A is in the right hand side. The right hand side says that this is all the A, so just one in this is. Questions? Is it clear why? Okay. Yeah, it's also an easy exercise to prove this directly. That such matrices are probably, but it also follows from this. Yeah. Okay. So we're done. Let me just say a nice corollary is that we get from the multiplicative domains. And again, I'm going to use it maybe in the, not maybe for sure, I think, in the third part of the course. But this is a very useful result of Tomiyama. So corollary, Tomiyama,
Just how you think you should spell them.
right. Okay, let me give a quick definition before I start. It will be easier to write it. Definition, let B be a sister, or maybe B be a subsister algebra of A, but B contains the identity of A. The sister algebra. A projection from A to B. This is something I'm going to use a lot in the second part of the course. In the third part of the course is a linear map.
Guy, I'm sorry to delay you, but I still didn't completely understand the last implication. But assuming like using this, why this would imply?
I'm just saying using this, and I mean this is something you should have proved last time.
Yeah, this I remember.
Once you know it, I think it tells you that A star B, where T is just a scalar, is greater than 0 if and only if A star A is less than TB. Because divide everything by T and use this and come back.
Okay.
Now you can take T to be 0. And this tells you, so if A star A is 0, A star A is positive. If it is less than or equal to 0, it means that it is 0. And then A has to be 0. Okay? Okay, this is one option. Another option, which is also fine, is to prove it. I mean, it's really easy. Show that, a new exercise, show that 0A, A star B is greater than 0 if and only if A. I'm just saying that it perfectly follows from this.
And here you're using again the Schwarz inequality.
Well,
to say that the bottom right thing is positive. You need B to be positive.
that this is positive?
No, that the lower left right thing.
This is positive?
Yes.
Yes. You're saying that I need to use this, the positivity of that?
But it's okay.
I don't need to use, okay, it follows from the Schwarz inequality, but I don't need to use it. I know it's positive since the Sol matrix is positive. So
okay.
any
Yes, fine. Okay, no.
Okay?
Mm-hmm.
I'm just saying whenever we have a 2x2 matrix that is positive, then it means that this is positive. And well, we know to say things. For example, if this is 0, then we know that this has to be 0 as well. And again, the techniques are linear algebra, nothing special. Just linear algebra. You prove it with for matrices with entries in it. Okay, so let be this. A conditional. I'm showing what is a projection. A projection is a linear map E from A to B, such that E restricted to B is nothing but the identity of B. A conditional expectation is just from A to B is just a UCP projection E from A onto B such that E of B1 A B2 is B1 E of A B2 for every A in A and B1 B2 in B1 in different words such that so E is a bimodal map. So whenever you're in this situation, then you can think of A as a B bimodule, because B acts on A from both sides by multiplication. And a conditional expectation is a map that preserves, there is a projection that preserves this structure of B bimodule. So I multiply it from both sides in elements from B, and I can plug them out. So surprisingly and very usefully, the following theorem, again due to Tomiyama, let us be in this situation. E from A to B, a projection, and on to B. Then the following are equivalent. So, okay, I'm going to prove just that one is equivalent to 2, but I'm going to tell you that there is also a trait. Maybe we'll prove it in another time. But one is conditional expectation. And 2 is UCP. So once you're UCP, then automatically you're conditional expectation. I don't need to require this. And this is something very nice if you think about it. It tells us that in the category of C-star algebras with UCPs as maps, whenever we have a projection, then it behaves like if it were in a much better category, like if it were a map of a bimodule object, which is really cool and really useful. And I will say at the end what is the third characterization, which is even better. But I'm going to prove only 1 and 2. So proof. So of course 1 implies 2, because by definition. Show 2 implies 1. Then what's the proof? I mean, a hint, this is a corollary, I call it the theorem, but this is an immediate corollary from the multiplicative domain thing. So I have here a map E. So I'm claiming that just by being a projection, it means that B is in the multiplicative domain of E. Because it's the identity on B. E, because it is a projection, is the identity on B. In particular, it is multiplicative on B. This is sister algebra. The identity is multiplicative. Right? So it means that B is contained in the multiplicative domain of E. Obviously, B is in the multiplicative domain of not B. But now just use the previous theorem by for every B1, B2 in B and A in A, E of B1, A, B2 is, first we use the left and then we use the right. Right, we're in the intersection of the left and the right. This is because we're in the right in RE, and this is because we are in LE. And we're done. There's nothing here, and it seems to be like an empty theorem, right? But it has a lot in it. What's the third one? In fact, it is enough to show that something like A is contracted. But maybe if I need it, maybe I'll prove it later. I don't know. But I just wanted to give you like sort of a useful application of the multiplicative domain. And now we're ready to start spring relations here. Some questions so far? Okay. So Steinspring Steinspring's dilation theorem. And let A be unit of sister algebra. I from A to B of H completely positive. Then there is a Hilbert space K phi. Unit of star homomorphism. Pi phi from A into B of K phi. And a bounded operator V phi from H to K phi with phi 1 norm equal to V square norm, sorry, V norm square, such that phi of A is V phi star phi phi of A. So let's say a few remarks. One, let's read this theorem in case I didn't say that I require phi to be unital. But let's read it for a second in the unital case. If phi is unital, so it's UCT, then what happens? Then pi is unital by the theorem. The theorem gives me a unital pi. So here I have V star V. So I have V star V equal to 1. So it means that V phi is an isometry. If phi is unital, then V phi is an isometry. And what? Okay, so this is one thing I wanted to say. And if we think, and then we can think, of H, we can identify H and V phi of H. So we can think of H as if it were sitting in K phi, right? As if it were a subspace. So we can think of H as a subspace of K phi, and so that the theorem tells us that phi of A is in fact pi A pH, in orthogonal projection onto H, pi phi of A restricted to H. Under this identification, it's just a projection. So i.e. Pi phi is a dilation of phi. is a dilation of phi. That's the reason we call it sine swing dilation. And if you want me to, so in this case, the theorem says something like this: for every phi UCP, there is phi scalar such that phi is phi. Something in the metric field. So that's the way you should think about this theorem. This theorem tells us that every UCP is just a corner of a star representation. Two, if the dimension of H happens to be 1, then and we're still in this case, and still finite. Then, what is V-phi? V-phi is just, right, it goes from C to K-phi, so it is just a choice of a unit vector, if it's an isometry. So V-phi is just, right, it goes from C to K-phi. It's just a choice of a unit vector, psi-phi. Right, it maps 1 to some psi-phi. And you see that psi-phi psi-phi be nothing but right, psi-phi we say that this is K-phi. This is nothing but V phi of 1, pi phi of A, V phi of Y, which is nothing but 1 by V phi star phi V. A, V phi 1. This is nothing but 1 phi, which is phi. So what did I say? I just wanted to say that we get the usual genus. And this is the good old genus. So the genus is just a private case of standardization theorem where H is when H is one dimension. And since the proof is going to be very similar, I mean, we can either do it quickly or just go, maybe I would just skip some details and tell you the structure. It's going to be very similar to the genus, but do you want to see it like every piece of it or half or none? Just the important points maybe. I think.
I prefer to err on the side of caution and show it off.
You what?
Prefer to err on the side of caution.
Prefer to
Err on the side of caution.
On the side of quotient?
Caution. זהירות.
אתה רוצה שאני אעשה את הכל כדי שאני אזהיר. אוקיי. קושן, זה קושן. זה הולך להיות קושן. Okay. Okay, so I'll tell you what. let's go over it. And in some places, maybe I will tell you this is very similar. There's nothing to be afraid here. And maybe in other places there will be. Okay, let me start. Okay, oops. So as in the GNS, I'm going first to construct K-phi, then to construct pi-phi, and lastly to construct B-phi. So defining K-phi. Do you remember who was K-phi in the GNS case? Or H-phi, we called it back then because.
A tensor H.
No, who was then, not them. There wasn't an H. It was
like a quotient from
it was a quotient of A.
to
So we construct a sort of an inner product, right? A sort of a sesquilinear form out of phi, and we took like the sometimes people call this Hausdorff completion. The Hausdorff completion of A, like we kill everything that this inner product needs to kill so that it will be an inner product, and then we complete it. Okay. Here we're going indeed to take the tensor product, as Aaron said, and consider the algebraic tensor product. So I was good with tensor product, so is this okay?
Not so much.
Not so much. So okay. So I will tell you what is a tensor product, but then I mean you should go and spend 10 minutes in Wikipedia reading this at least. Okay. So what is algebraic tensor product? I mean you can do it in many categories, but let's pick just for I don't know for vector spaces. So more or less what you do is you take the span of all the formal elements of the form A tensor psi and A sin H, span over a field, in this case C of course, but then you mod out by some relations that will make this to be linear in this coordinate and linear in that coordinate, and so modulo a relation, I don't know, twiddle, where A tensor psi plus B tensor psi is equivalent to A plus B tensor psi, and A tensor psi plus A tensor eta is equivalent to A tensor psi plus eta. And maybe I need also something like lambda A tensor psi is equal to lambda is equal to A of lambda psi, which is equal to lambda of A tensor psi. Do I need something else, or you think this is enough? Good? Right? So you define these relations, and then you take the quotient under these relations, and then you get something that is called the tensor product. So it's good to take a few minutes and read about this. Of course, there are better definitions. I mean, that's a constructive definition somehow. There are also more categorical definitions like universal objects such that blah blah. Okay, so consider the tensor product and define sesquilinearity and define a sesquilinear form on it by A tensor psi times B tensor eta is eta phi of B star A psi. And extend here. Note that this is It's just positive. Is a positive definite. The Squirinian form, and this is very important. Why is this positive? The reason this Squirinian form is positive is exactly that phi is completely positive. Why? Because if right, if you take an element of the form AI tensor xi, and let's do it like this. Then this is nothing but right xi1 until xin times the phi n acting on the matrix AI star Aj acting on xi1. So here is exactly where complete positivity enters into the picture. Now we use the thing. Now we continue as in the GNS. I mean that's the end more or less of the proof, because now we continue as in the GNS. So we're going to define the n phi to be the kernel of this sesquilinear positive semi-definite form, and to take the quotient and to complete it. This will be our k phi, and then we do what we have to do. We define pi phi as we have to do, and v phi, and we'll be done. But now it's a good time for a break, and so let's take a break. Finish it? Question? No.
Konstanzflüge ist ja gar nicht. Money? It's a double action. גם action וגם V. גם הגיע, כן? אלכס גם הגיע, בטח.
איפה בארץ?
הצלחת להזיז בסוף.
מה?
הצלחת להזיז בסוף.
את מה?
רגע, בארצות הברית. לא. זה 4:17.
ראית שאיחרתי ברבע שעה.
כן.
הוא תכנן.
יצאתי רבע שעה מוקדם מהפנסמינה.
לא אמרת שאתה רוצה להזיז את זה
לא, אמרתי שזה היה בשני ואני רוצה להזיז את זה להיום.
אז רק שהצלחת.
כן, הצלחתי.
כן.
כן, אבל זה עדיין לא נוח, זה פחות לא נוח ממחר.
כן.
זהו, לקחתי, פשוט הסתכלתי בזה, רציתי ליצור על המפורסמים האלה, ולמצוא בקונטקסטים, אני חושב שזה סיפור יצא ממקום של יש איזה סיפור טריינגולית.
יופי, הוא עושה את זה טוב.
אני מקווה עוד לא חושב שכן.
הסתכלת על זה?
כן, הוא מזכיר את צור, לא מוכיח.
לא.
כן, יש לו מאבק של שחר עוד מישהו. אני לא רוצה לקחת מיינוס 1.
כן. ואז איכשהו דברים, עכשיו דברים נגיד. כשאתה עושה את זה לחברות כלליות, יש לך כאן איזשהו שפיל כזה, דברים לא מדייקים.
כן.
שבוע הבא נראה.
כן, עכשיו זה מוצלח, אני יודע.
לא.
שבוע הבא.
Sounds like
זה תמסיס.
שזה עניין, אבל בעצם כל פעם שני
זה אוקיי, תלוי כן. אם אתה ניסה לכן רק רעש סי. לא, משהו. יש לך רק פאול. יש לך רק פאול. לא, 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 לא. ממש פשוט. שהאי ספייסס. לא, צריך פה משהו. לא, חייב. איזה ספן? C ספן או R ספן? C ספן של הפאולי מטריסיס והאידנטיטי. אז כן,
לא, יש לך שורש...
אתה לא רוצה כאילו C ספן, אתה רוצה מכפלות של פאולי.
כלומר, אני מסתכל על סיספן שם.
למה אתה מסתכל על C ספן של פאולי? לא של...
אבל זה יוצא שמונה מפחיד.
כאילו...
על החברה מצוין.
כן, אם אתה רוצה... כאילו שערים אוניברסליים, אז אתה צריך לעשות... כאילו, אתה רוצה לקבל כל טארי או בלי סבירה. זה גם לא מעניין. זה עוד דווקא מותר. יכול להיות שאני מבין ככה.
לא, אני צודק, אני סתם משהו קטנה.
אם הם מנורמלים, אז כאילו אין לך סיכוי, כי כאילו, אם אתה רוצה שמישהו אחד יהיה יותר נמוך, אז כדי שזה בסוף יצא מנורמל, אתה צריך שמישהו אחר יהיה יותר גבוה, איך
כן, זהו, גם סלאק. כאילו,
הנקודה היא כזאת, אוקיי, אני מבין את הבעיה שלי. הנקודה היא, בגלל שהם לא תיאוריים, הג'יונט שלהם יהיה פריק. מה שצריך לחשוב עליו זה דווקא משהו בממדים יותר גבוהים, לא חד ממדים. אז הנה, אז אני יכול לעשות לך, הנה, מאוד פשוט. אני מגדיר לך להגיד לך שני סטייטים על M2. סטייט אחד זה הטרייס, וסטייט שני זה הקורדינטה האחד.
אני אף פעם לא רוצה להקשיב.
זה לא זה, אבל סיסס זה מאוד...
לא,
זה ברור שהשני הוא סטייט?
כשקורדינטה אחד היא סטייט היא פיוסיפימט.
כן, זה it's a projection you כאילו,
לא, IRS סייטרלי.
רגע, ומי גדול ממי?
הייתי פעם...
טרייס גדול.
אז זהו, לא, אבל הטרייס הוא מנור, אתה צריך לנרמל את הטרייס. חייב לעשות חצי הקורדינטה 1-1 ועוד חצי הקורדינטה 2-2. ואז פתאום, כשתחסיר ממנו את הקורדינטה 1-1, אז אתה פתאום יש לך מינוס, זה פתאום מינוס חצי. זאת אומרת מה אני אומר?
כי זה לא טבעי לעשות את זה בסטייטים.
ומה? על לא מנורמל? הבנתי, אוקיי.
לא, אבל רגע, אולי זה כן. אם אתה מנסה עכשיו מה קורה במדינת, אולי זה לא טבעי פשוט בסוף במדעי.
מה שכתבת לי, המאמר,
מה?
הם הוכיחו במקביל וקצת לפני את התוצאה, כאילו, המקרה קלאסי?
כן.
אז למה לא שמענו על זה?
אולי סתם כי אנחנו מקורבים לאנשים.
כאילו בעולם זה יקבלים יחד.
נראה לי שכן.
בעצם, כן.
לא יודע, בבלוג של גיל קלעי מתייחס לשניהם באותה.
לשניהם אותם.
והקוונטום דיספי זה כאילו גם מה שעשיתי בתזה זה כאילו זה פתר
זה אכל
חלוטין.
כן. כאילו זה
מה זה
אכל?
אכל? כאילו אני ניסיתי לשפר איזה משהו קיים, או לא יודע מה, זה לא רק לשפר, זה פתר את הבעיה.
פתר, אין בעיה.
אין בעיה יותר, יש עדיין את השאלה של האם יש locally testable, כאילו כמו שהיה בקלאס, זה הביא את המצב הקוונטי למצב עכשיו ה-state of the art הקוונטי, הוא כמו ה-state of the art הקלאסי עד לפני 3 חודשים.
בקלאסי יש locally testable.
מעכשיו, לפני זה לא היה.
בקוונטי
אין עדיין locally testable.
אבל הם עשו ביחד את הקלאסי.
באיזשהו מובן מצחיק, הם בערך פתרון דומה, פתרת locally testable classical code ואת ה-quantum code, אבל כבר לא locally testable בקוונטי.
כאילו מה הסיבה המוסרית?
אני לא יודע.
אז אני מניח שמהר מאוד תהיה התקדמות.
יש להם גם, כן, אני מניח ש...
כאילו זה עכשיו.
נכון.
עברו איזשהו מכשול
נראה לי שכן.
קונספטואלי.
אני מאמין שכן.
ומה הרעיון שלהם?
אני לא יודע, אני יכול להגיד לך ממש בזה, אבל...
ממש בזה.
מן הסתם יש צ'יין, הם כן בונים קודים מ-chain complexes, כמו כאילו קודים הומולוגיים, מה שנקרא.
קודים הומולוגיים.
מ-chain complexes הם קודם כל...
איזה הומולוגיזם? שנייה, ראשונה?
שנייה, אני חושב.
אוקיי, שזה מבחינה קונספטואלית כאן הפריצת דרך הייתה של לוברוצקי וגוץ.
נכון, למרות שהקן קומפלקסים האלה הם לא גיאומטרים במיוחד, אני לא חושב שהם גיאומטרים, הם מגיעים, זה כזה גרופ קומולוגי, שזה כאילו גיאומטרי, אבל זה לא בדיוק גיאומטרי.
אבל איזה חבורות?
נון-אביליאן.
אבל
לא, סתם, להפסיק את זה לפני שאומרים
כאילו זה ה...
לא, כן.
ברור לי, אבל כשלא נביליאן הכוונה זה הייזנברג, זה אוקיי.
כן, כן.
essentially ביליאן?
כן, אז זהו, אני לא יודע מה, אני לא בטוח.
איזה למפלייטר?
זהו, אני לא יודע מה חבורה. אנחנו עושים איזושהי בנייה שהם קוראים לה lifted product, שזה די דומה לדברים קודמים שעשו במובן הזה שהבינו באיזשהו שלב שטנזור פרודקט של chain complexes יכול איכשהו להשאיר תכונות טובות באיזשהו מובן, פה יש איזושהי בנייה אחרת שנותנים לשם.
זה לא דומה לבנייה של החברים שלנו, הדאבל קליגרף.
לא. מי זה? מי?
לא, לינור...
אין לי מושג מה.
אתה מדבר על ה-QLP?
על הגרסה כשפתרו אותה... שמעת גם שהם בעצם פתרו את הקלאסי, נכון?
כן, כן, הם אומרים, הם בונים קודים שהם רובסט, כאילו טובים קוונטית, אבל שהם גם פותרים.
וזה בדיוק אותה תוצאה ש...
זה בדיוק אותה בנייה, אבל?
לא אותה בנייה, אבל כתוצאה זו אותה תוצאה בדיוק כמו...
אבל הציורים שם נראים מאוד דומים.
כן.
מציירים כזה מלא סקווירס, וזה נראה מאוד כמו מה שאתה לא יודע, עירית שמה כאילוסטרציה. אני לא יודע. אבל נראה כתוב יחסית מתאים.
שניהם עושים הומולוגיה שנייה, אם אני מבין נכון. נכון?
שניהם עושים מה?
משתמשים בהומולוגיה שנייה כדי לייצר את הקוד. בניגוד לקלוד את הקודים יותר קלאסיים. זה הריבועים את שאתה רואה.
נכון. כן, נכון. אבל כן יש לי תחושה שאולי מה שהם עשו זה שעירית, כולם יהיו יותר גיאומטרי קצת.
יותר גיאומטרי מצד אחד, מצד שני, הם לא חשבו על זה הומולוגית. אני יודע כי שאלתי את אלכס, ולכן לדעתי יכול להיות שראית הקוטציה שלך שהם עשו יכולה לעשות במקרה הבא.
אתה אומר שהוא
לא למדתי את העבודות האלה, אני לא יודע, אבל הקוד שהם יצאו הוא לא קוד הומולוגי.
כן.
הוא לא מוצג.
כן.
אבל אם היית מציג אותו, אז מה שנראה סביר שאפשר לעשות, אז אני מניח שהיית יכול לתת לו אינטרפרטציה לקוד קוונטי.
כן. נכון. בעצם נכון, בעצם כל chain complex הוא קוד ורמה שאתה בוחר הוא כבר קוד קוונטי.
אבל העבודה שמוכיחה בו, כל מיני תכונות קלאסיות טובות של מן הסתם. אוקיי, אני מסתם.
אתה צריך אולי לשאול באמת, נגיד את אלכס אולי לשאול מה...
אני חושב שהוא
בטוח חשב על הקוד, על מה שהם עשו וחשב, והיה לו בראש גם מה זה אומר קוונטי. באופן?
כן. נמשיך?
So okay, so I do wish to finish this, but in some points the things are too similar to the GNS than I'll say it's needed. Okay, so we let n phi to be this set of all elements in H and so H, such that you use 0, then in fact, just as we did in the GNS, this will be the same thing as the set of all these tensor H, such that U times V is 0. So in particular, this followed by the Schwarz inequality. And the industrial sesquilinear form is a linear product. The induced sesquilinear form on A tensor H mod n phi is a inner product. So that's K phi with its completion. And you can write a note to yourself that if both A and H are finite dimensional, then K phi will be finite dimensional, and if both A and H are separable, then K phi will be separable, right? But okay. So defining pi phi. Do what we have to do. So if A is in A, define phi A from A tensor H into itself by phi A of what it does to a sum like this. The only way you can multiply it. And
without the A on the right hand side, without the pi on the right hand side.
And we need to check that it is well defined, right? And so let's check it is well defined because okay, this is maybe the only important part here, and everything follows. So what is so note what is pi A of AI tensor psi I times pi A of AI tensor psi I like this. But none of them will have to be today eventually. This is AI and psi I, AJ and psi J. And this is what, again, this is nothing but psi 1, psi n. of phi n of AI star, A star, A, AJ, psi 1, psi n. Now, so, or maybe let me write it, please. This is less than or equal to. So, do you agree that I can take this out in norm? So to do something like this, A star A, psi 1 to psi n of the AI star AJ. Do you? I mean, there's something we need to justify here, but this looks like things we did a lot of time, right? A lot of times. Okay, so maybe we can discuss about it in a minute, but okay, but now go back. I mean, and this is nothing but star A. Tensor psi I, tensor psi j. So when this is zero, so it is well defined, and in fact, this shows also it is an isometry. Maybe I should think like this, because this is after there. Yeah, so these guys are okay. You know, I mean, I identify them with their image in the quotient, but okay. So does this need an expression? So okay, so from here, pi A is well defined, and plus isometric.
It's bounded, so extends to the completion.
So it extends to the completion. This is what I want to say. No, I just wanted to say it's. I didn't do it on the quotient. Okay. So sorry. Sorry, I thought I defined it already in the quotient. I think fix it for a second. But I just put here all these guys need to be in this kind of square brackets, and yes, and so it's not. I didn't need to say it's well defined. So I can say something else. So pi A of n phi is in n phi. So pi defines a map of A tensor H and phi itself. This map will be bounded as well. Hence, we extend to pi A in B of the completion. Does this make sense? I think yes. Okay. So plus, easy to verify, phi from A to E of K phi is star. Okay, there is nothing to do. Just okay. So that's the place in which you might want to ask me, Guy, do we have like a counterpart? So okay, so when we prove this in the GNS case, then we noted that when phi was pure, then in fact phi was irreducible. And I also mentioned, because we didn't prove a Cadison transitivity theorem, but I mentioned that so irreducibility is also algebraic irreducibility. So in fact, you don't really need to complete this space. You get it for free. The fact that it is complete in the GNS case. Just because you can't have an invariant subspace if map is irreducible, even if it's not.
In the GNS case, you say you never actually need the completion?
Yes.
Yes, for a pure phi, I said it, but I didn't prove a Cadison.
Okay.
I didn't prove this. I just mentioned this, but we did prove that when phi is a pure state, then pi is irreducible, or even only if then pi is irreducible. So a question that we will answer later: what happens in this case? What are pure UCPs? And and what is the correct definition that will give us that pi is irreducible representation? We'll keep it in mind. We'll get it. Oh. Lastly, okay, here there's really nothing to do. Maybe I'll just say just to finish the theorem. So defining proof, defining V, defining so and I skipped this part. Is it clear? I mean, or do you know at least how to prove it? So you have a big matrix, right? This is a big matrix, which you can decompose as sort of do it. It's a good exercise to write it as A1 until AN and then zeros. And then a matrix, I think that will look something like this. And then a matrix that will look, so this is with star perhaps, and this is without star. So this is this matrix. And then we know that whenever we're in a situation where we have x star y x, and y is less than or equal to z, then x star yx would be less than or equal to x star zx. And this one is of course less than or equal to the norm a star of a star a times the identity map. So okay, we did this a couple of times, so I guess you know this. I'm just mentioning it if you will want to add the details at home.
I think maybe if you introduce the scalar valid matrix, the scalar matrix which
Once it's a scalar, yes, you just can push it out.
yes, but you can write a scalar which is the norm a star a as a sum of a star a and something else positive.
Here you mean? No, I don't see.
I mean, you can write the scalar matrix with the norm a star a
Yes.
on the diagonal
Yes.
as a sum of a star a of this one and its complement. Both are positive.
Ah,
And they compose
sure. I'll define this. I remind you it goes from H to define define v phi of psi to be 1/8 tensor psi in the quotient. So and verify that v phi of square is phi 1. This is easy, and v phi star. Okay, this is all immediate once you define it like this. This is the same thing as the things. Okay, so we're done. But this is not the end of the story. So it is a big difference from the GNS. The remark, we have more than remark. Okay, maybe the one that I mentioned before, if H and K are H and A are separable, and so is fine. 2, in case in the GNS case, in case H is C, then so what is pi phi of A of v phi of H? So this is inside a case, of course, right? But in the GNS case, we checked and we know that it gives us everything. In other words, that the vector we chose was cyclic, right? This is not true anymore. In general, anymore. I mean, when H is not one-dimensional. But we can fix this. So, but we can fix this. So let's fix it artificially. I mean, let K phi prime be pi phi of A of V phi H closure.
Can you explain why it's not equal to K phi, at least in the explicit construction we did before?
So
don't you get all like elementary tensors? So it is true.
no, so the thing is, in some sense, it is similar to these ideas of when you have a tensor product of things, then suddenly things are not sitting rigidly in the tensor product, similar to Butenau, the problem we have discussed it. What happens is that this space.
You say things are entangled.
That are what?
If you say things are entangled, you seem to be smarter.
Okay. So things are entangled, yes. In the basis language. No, so the problem is exactly this. This thing, this K phi prime doesn't sit inside the tensor product. Okay, there is a modulo something, but never mind. In the tensor product in a nice way.
Why?
Well, it doesn't have to, right? So if one of them is one-dimensional, then suddenly it has to sit. Now,
Okay.
can you see it?
Sorry?
I mean, if one of them is
Yes.
one-dimensional, if a tensor in the
Yes,
tensor,
yes. Okay, I see what you mean.
Okay.
Sorry.
and we will see examples later on. Don't worry. I mean, we will. I can give you in 10 minutes of really easy examples out of it, but don't worry. Right now, I just want to mention something. Okay. So and now I can replace everything. I mean, so now I have a new space. It sits in an original space that was weird, but now I have this space, new space, and I can define, and we can verify that pi phi. Okay, this is immediate, right? Pi phi of A of A K phi prime is in K phi prime. So we can think of pi phi as going from A to B of K phi prime, and we have a V phi from H. So V phi prime from H to K phi prime. That's what it needs to do, and so my point is that check that. So, okay, I mean, this is clear what is V phi prime. It's just V phi. I did nothing. I mean, this is just V phi, but I know that at the end I'm sitting in a smaller space. So I'm just restricting the range into a smaller subspace. This is what V phi does. I mean, it's nothing. And now just check that it is a GNS construct. I mean, it satisfies the GNS theorem. So D star pi phi of A V phi is phi of A. Now, suddenly we have a uniqueness theorem. So such a Stein-Sprung dilation is called minimal. So in the GNS, we had this part in the proof where we said that the GNS is unique up to something. So now I want to have the same uniqueness here, but I needed somehow this minimality.
Okay, Guy, maybe I'm still a bit confused, but please stop me if it's trivial, but is this thing even a, so as you wrote it verbatim, I'm thinking of taking all A's in the algebra, taking all Xi's in H, and looking at the expressions you get by applying A on the representation of A on this V phi of H of Xi, right? I mean, this is a subspace. And
once you believe me that pi phi is a representation,
yes,
is a star representation, then I can take the what do you mean by subspace? I mean, you mean
what this object? I mean, what as you wrote it
this
here.
is subspace. So what's the problem?
So
you don't see why it's closed under sums?
Yeah, maybe I'm stupid, but I don't. Yeah, I don't see why it's closed.
Okay, so that's an exercise. I mean, if you want. I mean, okay, you're right. In
Somehow,
some
if
sense.
it's
no, I'm
close down the
joking,
sums,
you're right. So
it should be
no, it
K5.
is. It's fine. I mean, there's nothing to.
Okay.
This is fine. But you're right that maybe in a justifiable way, it was better to write your, I don't know, span and then close it. And then tell you can erase the span if you want.
But then it should be all of K5. No, this is what's confusing me. I mean, K5 was the algebraic tensor product of stuff from A and H, taking a span and then taking a closure.
They taken K5
was A
tensor
tensor
H.
taking, so it's like finite sums of elementary tensors from A tensor H.
Yes.
Taking finite sums, then taking a closure. No, I mean, what I'm trying to say is that in the specific proof, we did build a minimal Stein spring dilation.
You claiming that the dilation in the proof is minimal?
Yes, this is. I mean, I don't see otherwise.
That V5 takes Xi to one tensor Xi. So why do you think that the image of V5 is so large?
Because you're taking all of its images on the pi A and then taking closing it up as a subspace and stuff.
Because then when you say when I do it with pi A, I act only in the left coordinate, so I can get all of A.
Like I saw your remark of the difference between the one-dimensional and the general cases is more like in the one-dimensional case, all tensors are elementary, but in the general case, you need to take like linear combinations to even get a subspace. Anyway.
Sorry. So the point is, sorry.
Maybe I'll say again what I meant, because it's not really, I just said that in the proof, we constructed the minimal Stein spring dilation as it is, but in general, you showed us that any dilation would contain a minimal one, right?
Then that's not no different than the GNS.
No. So you're saying
Yes.
you're saying what I constructed was minimal, and I'm. Missing something now, but give me one more minute. No, I don't see it. I mean, why?
If I believe you, I mean, if I
Okay, you know what? Okay, so maybe it's better to
Later,
I want
sorry.
to finish.
Yeah, sorry,
But
I
we can
just-
discuss about it later.
Yeah.
I mean,
okay, sorry.
okay. Okay, so I owe you an answer regarding this, but just let me write the claim anyway. Trivially true in some sense. Any two minimal sky-string representations relation, sorry. I phi prime, K phi prime. And V phi without prime and one with. Of a UCP, of a, not UCP, CP, 5 from A to B of H are unitarily equivalent. So, meaning that there is a unitary from K prime to K, such that right, such that everything for me, such that I prime of A is equal to phi of A, you read star here. And also H sits in them in the same way. So you are B prime is V. Okay, and there's nothing to prove. I mean, because you act on, because now that you know that K prime is of this form in K, then just write it. Just verify, just define the unitary to take pi A V C to pi prime A V prime C, verify that it is well defined, and it will do the job. So proof just I mean, there's one way to define U. There is one way to define U correctly. Do it and verify it's a well-defined unitary. Satisfying. This and that. So this is just like we did in the uniqueness part of genus. Okay. So now yes, I mean, there are many nice applications we can get. For example, so right, we showed that you remember that that we had this map rho t that there is UCP. Well, we showed it is positive, but using there is a positive map. Rho t from continuous functions on the circle into like for t contraction, mapping p plus q polynomials pt plus qt star. Right? So this is something we did last time, and I mentioned that today that since this is a commutative C-star algebra, then this map is automatically UCP. This follows from what we showed about commutative range, so domain. So rho t is UCP. But so let's take a minimal Stein spring of this rho t. What will it be? So let's pi k v be a minimal Stein spring dilation of this rho t. This is a map, right? Pi. It goes from continuous functions over t into v of k. But this is a star homomorphism. So it takes z to what? So z star, z is just the function z, right, on the circle. So z star z is 1. So z and z star is 1. So z goes to unitarian v of k, right? But it's much more than that. So okay, so this like shows that. Okay, so let's write this explicitly. So for any, I mean, I write p plus q bar goes to p of t plus q of t star. Do you agree that instead of doing this, I will write? I mean, it's more helpful to write it like this. For any polynomial in z and z bar, p goes to p of t, where we agree that whenever I have z bar, then it means that I do t star. So we know, okay, so we know that, right, and this map is unital. So if this map is unital, then this V is an isometry, right? This is something we explained today. And you can think of H as sitting inside K, because it's an isometry. You can identify H and its image inside K. So this shows, rho t is nothing but rho t of any function in CT is nothing but compressing into H this file. So in particular, apply this to on this polynomial Z prime, and you get that P of T will be P of H of P of U. In particular, T to the n is P of H U to for n. Okay, but not only that, we know that this unitary dilation of T is also unique in some sense because of the uniqueness of the minimal Steinspring theorem. We also know that this unitary U is unique in the following sense. So if you so K is I know the span of U and H. And psi and sin H. And Z. I can think of it also as the sister algebra generated by U and U star acting on well, by U acting on H closure. And for any other, unitary dilation, such unitary relation, U prime and K prime of T maybe it's better to write such a minimal unitary relation. There is a unitary V. Well, you know what you got, right? From K prime to K, such that. Okay. Now, again, so the picture that you should have in mind now is that, again, the continuous functional calculus told us that, for example, if we have a unitary, then that for any unitary we have this map rho T that goes from continuous functions on the spectrum of it, or in particular for T, if we set that contains this value into B of H, that allows us to do the continuous functional calculus that we can evaluate on polynomials and continuous functions, etc. This was a star homomorphism. Now that we're dealing with contraction, we have the second best thing, which is not a star homomorphism but a UCP, and we can think of it in two ways. One, like we got a direct proof that this UCP is that we have such a UCP that behaves well on polynomials. But in another sense, using Steinspring, we can think of it just as a compression this star homomorphism, of the star homomorphism that we knew before that allows us to play with continuous functions and over the circle with unitaries. Okay.
I don't found the graph, but
What?
I mean, I want to make a mapping. Maybe we can check it together afterwards. I think this K is also could be thought of as an inverse limit of H when you have T up. I mean, you have the map H to H to H to H with T. You take the inverse limit of this, and this inverse limit T becomes
I completely agree. Yeah. So I think it's even
We actually kind of did that, right?
what?
When we proved this theorem directly, we kind of did
Exactly. Yeah. So you're right.
that. Direct and
But that's a good exercise to write this if you want. I mean, to verify this nice observation. Okay. Sorry. I erased the. Sorry for that. You have it recorded. Okay.
no, this is not what you wrote last week.
This is not my. No, you sure? I
I
think.
think you wrote there. Never mind.
Okay. Okay. No, but okay, you're right. So it does make sense. So yes, so now we are again, so we showed last time that functions from commutative C-star algebra into an operator systems are positive if and only if they're completely positive, and same for functions from an operator systems to function systems or to commutative C-star algebras are positive if and only if they're completely positive. And we said, okay, commutative C-star algebra is one thing we need to check, and we checked it. Now the next thing we need to verify that we understand is n by n matrices over the complex numbers. So maps into Mn, and we'll also use this result later in Hobson's extension theorem that we're going to the next step. Okay. So so theorem, or maybe before theorem, let us play a game. Okay. So let S in A be an operator system. And EJ standard basis. And if A, well, if T is a matrix of n by n complex numbers, then of course I can take the ij element just by take well, TEJ right is the jth column, and then I can multiply it by that. And if P is a UCP is just a map for now from S to Mn, just a linear map, we can define F sub phi so this is going to be a map from a linear map from Mn of S into C in the following way. So F phi of the matrix Aij is one over n and the sum of phi acting on the ij's entry. So the ij entry is an element in this operator system. So this gives me a matrix, but then I take the ij element of this matrix. The way to think about it is like this. This is, as I said, as explained before, this is nothing but EI phi of Aij Ej. Or if you want, let's call it, I don't know, E of phi n of the matrix Aij of E, where E is this huge vector E1, E2 until En.
Normalize.
And over. So this is not, I mean, okay, what's really going on here is that I'm going to do some kind of tensorial identification, but I want to do it explicitly, not just with basis and everything. So we have a map. Phi goes to f of phi, and if we started, of course, with a bounded operator, then this will be a bounded linear functional. And also, we can go the other way around. Well, phi of f Aij, the ij's entry of f sub phi will be nothing but n times f applied on the matrix. So just this matrix where you have A in the ij's entry and 0 else. So again, I did something that in some sense I could have said it like immediately that we have an identification between these guys, but I wanted to construct this explicitly. Now, also know that okay, so know that F is unital implies that phi is unital and vice versa. And phi is unital and phi is unital. Okay, fine. Play. These are inverses of each other. I mean, maybe let's specify the. Okay, let me stop for a minute. There's something not canonical in this map. Okay, and thus we have this choice of the standard basis. This guy, in general, okay, in general. B of I know. Okay, you need to do it carefully. I mean, you need to explain what is the tensor product that I'm going to take. But let's say if at least if one of them is finite dimensional, then it is clear. So this thing say is isomorphic naturally to S tensor Mn star. And so, but here this is isomorphic unnaturally to S tensor Mn, which what did I want to say?
She's MNS.
Yes, this is MNS, yes, but sorry, there is I forgot to star in my, okay. I didn't prepare it. What did I want to say? I wanted to say that okay.
Actually, BSMN is isomorphic naturally to S star at tensor Mn.
This is you're saying this is what I wanted to say. Oh, thank you. Is this true? What? No.
Can.
Guy,
Yes.
is this some sort of tensor home adjunction?
Yeah,
Yes,
exactly
exactly.
right.
Exactly, this is what I'm trying to
Yeah.
figure out. Now, there should be something here, some identification. One of the identification needs to be unnatural, and all the other needs
Yeah,
to be.
this is the.
So this is this you're
first thing.
saying, and this is
S star tensor Mn star.
what?
Now we can add duality on Mn.
This
That's
is
the unnatural.
unnaturally. Thank you. Unnaturally, and then this is Mn over S star. Oh. Okay, theorem. So let S be an operator system living inside the sister algebra A, find a map from a linear map from S to M and linear. Then the following are equivalent. A is completely positive. B phi is n-positive. And C F phi is positive. Now, I'm stating this as a theorem, but there will be a special ingredient in the proof that that will be very important, and I will tell you what this ingredient is going to be. Okay, maybe I will tell you the proof in a nutshell, and I'll give the exact details next time because we don't have time anymore. So of course A implies B, and from I erased this, but from this part, you see also that B implies C. Right, this was F. So we erased everything, but the important part is that on the board. This was F of AIJ. So we have that A implies B and B implies C, and the only thing we need to show is that C implies A. And what's the idea? The idea is as follows. We know that F phi is positive and is unital. If phi is unital. Okay, let's speak for a second about the unital case. I didn't say phi is unital, but let's assume for a second phi is unital. Then this is a unital positive map. So if it is a unital positive map, then it's a state on ML of S. So it's unital contraction. So if it is a unital contraction by the good old Banach, I can extend it to all of A. For unital contraction on all of A. On all of, sorry, not of A, of Mn of A. Mn of A. But unital contractions on sister algebras are automatically unital positive. So this extension will be unital positive. Now, go back with this identification, but now you're on A, and you get, so okay, you get a new map, phi of the extension of this map. This will be completely positive, and its restriction on S will be this phi again. So it will be completely positive.
Show this extension.
This extension will be a state.
Okay.
And this state will give you a map that I claim will be easily seen to be completely positive on the sister algebra. And therefore on S. So okay, so this
so here you're using also that.
Here I'm using what?
That any positive map between sister algebras is completely positive?
Any positive map that goes from a sister algebra is completely positive.
This we didn't prove, right?
This is something we didn't prove, but
right. Okay, just make sure that we're using.
We discussed it. In fact, I'm not sure. Maybe we don't need this.
Okay.
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 We'll check it together next time. I just want to emphasize one thing. The thing I want to emphasize is that this part of the extension of F of a state to all of A will result in extension of a completely positive map from S to all of A. So we'll have a sort of this Banach argument for completely positive maps when the image is finite I mean for representation of finite dimensional Hilbert spaces. And this, at the end, is the essence of the general theorem that's going to be Armstrong's extension theorem, because what we're going to do next is to say, we have a representation, let's compress it on finite dimensional spaces, and there, okay, we need to work in the correct topology, and we do it, but it will be a topology, a weak star topology, and we will be able to take a limit point, and this will be the extension. So in fact, we're going to use we're going to use this fact as the crucial step next time. So okay, see you next week.
No.